The title of the talk is Gradient Descent Aligns the Layers of Deep Linear Networks. And this is joint work with my friend and colleague from my home institution, UIUC. And before I motivate the talk, let me just give you a tiny teaser. So bear with me for a moment, because part of you might be thinking, why in 2019 are we talking about linear networks? What's the purpose of this? So let me give you a little teaser. So let's say you download some data from the internet, and it's just these two circles and these two classes. And let's say we train a logistic classifier, just a linear logistic classifier. So for those of you that have not seen this before, it might be a little bit surprising. If you just do gradient descent on this, you learn the max margin classifier. I see that's maybe many people treat this as a obvious or given fact now, but of course the way I at least was trained was that in order to solve for the max margin classifier, I need to solve a specific, concrete, constrained optimization problem. But that's not true. You just run logistic regression, gradient descent, you find the max margin classifier. This is what it does. And what you should ask yourself is what happens if I do a deep linear network. So now a deep linear network, it's just an overparameterization with many layers of a linear classifier. So the classifier is just a product of weight matrices. So it's just linear function in the input. So what will happen if you run gradient descent on this deep linear representation, which of course we should be thinking about? This is polynomial optimization. Of course, it's only a multilinear form. It's not full polynomial optimization, but what's the solution you get? So what shocked me was that you get the same solution. Gradient descent doesn't care that it's not convex, doesn't care that it's a polynomial. It just finds the same solution. So the goal today will be to dissect this as much as we can. And I will actually give you the punchline right now without all the assumptions stated. But the punchline, which might look a little bit opaque, is this is the form of what we solve. So what's actually going on, it's not just finding the maximum margin classifier. It's finding the max margin classifier, which is even minimizing a Frobenius term constraint on all the matrices. So it's not just solving for the max margin classifier in the sense that the product of the weight matrices, that induced linear form, that vector, is an L2 minimal vector. It's even minimizing the Frobenius norm of all the individual matrices. Okay? So personally, I find this utterly shocking. This is the kind of thing that maybe 10 years ago, I would see somebody giving a talk that if you wanted to induce this sort of property in your optimization process, you would add a bunch of explicit regularizers. And I'm saying, no, you run gradient descent, and this is what happens. So maybe I can motivate the talk a little bit now. For those of you, including me, who might have seen a title like this a year ago and thought, why are people working on deep linear networks? I think many of us, we have essentially two reasons why we work on these kinds of problems. One is that we're kind of excited about the promise of deep networks. The other reason is the math is interesting. And for me at this point, if you threw away everything about this problem and just looked at this math formulation, it's already interesting. OK, so this is the theorem we'll get to.
Balances the Frobenius norms in different.
Yes.
OK.
And if you think maybe my and Zue's math has an error, I'll show you the plots, where you can just run this experiment yourself. I can give you the 4 lines of PyTorch to check it. Yeah. It's totally shocking for me. And there are people in the audience who would think, of course, but I'm actually still kind of confused and shocked by this. Oh, and another thing that many of you, maybe if you're bored and doodling or something, can think about during the talk is what aspects of this are true in the ReLU case. Of course, we'd all like to prove something strong about general nonlinear networks. I'm happy to field those questions throughout. I have become a slave to my GPU, and I have checked many of these things on my GPU.
Only one GPU?
So let me start with a joke. So as all of us know, I'm new to all this. When you do an NSF award, you have to write an explicit budget for how you spend your money. And I put a hardware budget in there. And I decided that, no, I will only get one GPU. But I am a slave to my GPU, and soon it is going to become a second GPU.
Exponential growth.
I'll go to 4 soon. Okay, so here's the outline of the talk. So that was the little teaser theorem. Then I'll discuss margin theory a little bit because we've seen a couple people introduce margins. I unfortunately missed Nati's talk, but I actually saw a picture of Nati presenting a picture of Peter Bartlett presenting a picture of Nati presenting. So I'm aware of some of the so I'm aware of a few of the things that have happened while I was unfortunately away. Also, Sasha presented about margins. Let me just give a few comments because for those who are maybe less familiar, it's of course not a panacea. You don't just replace your loss with this ramp margin loss and suddenly get a generalization bound. But let me just give you a few kind of perspectives, given that everyone has already benefited from so many explanations so far. So, like many people, I had a strong reaction to this paper. In my particular case, I was, like many people, just sort of chilling out in Berkeley at the Simons Institute, sort of relaxing, and I'm sitting in the front row. Actually, Sanjeev and I were co-organizing, I guess, the seminar there, and Sanjeev invited, I think that's how it happened, Sanjeev invited Ben Reck to come give a talk. I'm sitting in the front row, and he gives this talk, and it was very provocative, and I'm very thankful for it, for getting me out of my comfort zone. Sorry, I'm having click problems. One thing I want to say is that, so many people probably kind of zoomed in on one part of the abstract and reacted to that. The thing I zoomed in on was this explicit regularization comment, and just as a consequence of my training, I thought, oh, I've seen this before. I've seen this before. It sounds like margin theory. And let me just give a few comments about that. So if you do choose to try to resolve some aspects of this paper using margin theory, it's one of these situations where you solve a problem by introducing new problems that you haven't solved yet. So in this particular case, if we wish to use margin theory to explain something about deep learning, first of all, we have to prove that we actually have a margin maximizing algorithm, which for gradient descent, it's still open. And the other thing is that just by saying we're using margins, we don't have a good generalization bound at all. So as in Sasha's talk, there's a choice of norm, and we have not resolved this at all yet. So there aren't, unless I'm missing out on some archive paper, there aren't extremely convincing margin-based generalization bounds yet. Apologies to the people that have new ones that I haven't seen. So it is true that I'm proposing, so what we're doing in this talk is we're doing the algorithmic part. We're trying to say that gradient descent does find, in some cases for linear networks, a margin maximizing classifier, but there's still a lot of the story to complete from here. And I'm not saying that the rest of the story is done. So a few more comments about margins. So why is it a useful goal to work on, why is it useful to prove that we have a margin maximization? So my personal reason for finding, let me start this sentence over. So a lot of people, their goal in the generalization bound is to try to get the smallest number. You just produce a generalization bound, you calculate it on CFAR10, you put your number in your paper. Another perspective is we want our generalization bounds to be predictive. So I want my generalization bound to be reflective of what actual empirical generalization I see. So the observed excess risk. So let me just show you a few plots from this paper I did together with Dylan Foster, who's here, and Peter Bartlett, who's, I believe, currently sitting in the hills somewhere in Berkeley. So here on CFAR are the observed excess risks. So this means the test minus train error. And if you plot this, and you plot it compared to the Lipschitz constant of the networks, I'm just going to use the keyboard. If you plot this against the Lipschitz constant network, you'll notice they exactly line up. Okay? So Lipschitz constant network lines up with the observed excess risk. For me, I would say this means that the Lipschitz constant is predictive of the generalization performance. So whether or not the bound is good or not, we have this fact that we can look at the Lipschitz constant and kind of guess whether the network generalizes well. I should say that this plot is not cheating. There's no doctoring in it. Yeah?
At this point, I know like half a dozen properties which correlate. So patience.
Oh,
Maybe a dozen.
okay, so you're saying that,
Correlation is
Also, to add a majority about it, but the fact that Lipschitz concept is not sufficient to ensure generalization?
okay, yes. So, okay, so the comment is that, okay, so first of all, do you guys both agree or disagree that it's predictive?
It's correlated. I'm not sure.
Okay. Okay. Yeah, let me just show a couple more pictures, and then maybe we'll postpone this conversation. Yeah, I'm just trying to motivate the use of margins here. I'm not. Yeah, let me add to that. So if you're not completely convinced by this, personally, I find this question of finding the normalization to be really extremely difficult, and I guess more difficult than just proposing one of these bounds. Okay, as they've been so far. So let me give a couple more of these pictures, and maybe you guys can revisit your worries. So another reason I found these bounds to be very predictive, and this part is independent of this Lipschitz constant, is if you plot the margin distribution, which is you plot these output margins, and then I've just converted them into PDFs. So these are the distributions of the margins. You find some interesting patterns. So from this, you can see that the margins are closer to zero, so the problem is more difficult for random labeled CFAR. So again, I'm trying to say that these normalized margins are a good proxy for the difficulty of the problem. Issues with the particular choice of normalization and Lipschitz constant notwithstanding. And I should say that, so you can look at this paper for the details, but one of the plots that kind of shocked me the most was that so you can see on this right plot here, if you take MNIST and make the labels random and CFAR and make the labels random, the margin plots are on top of each other. And I tweaked the bound many times and obtained different versions of these plots, and they were always on top of each other. Yeah?
So this goes back exactly to the question you're getting at. What do you call margin here?
This is the normalized margin, so it's the,
Normalized by what?
sorry?
Normalized by what?
Well, in this case, it was the bound in that paper, but. So it's the margin, which is the distance to the next best class, and then that's divided by the full form of that margin bound, which was this one with this like ratio term and the Lipschitz constant and okay, yeah.
Do you think the normalization was important, or are you saying these trends exist for almost any reasonable?
Yeah. So here's a. Okay, so maybe I should also let me just make sure I understood the question. So the question is that, are these plots a artifact of the normalization we chose? Because again, I'm doing this normalized bound, and the bound, of course, as everybody here knows, is a very loose upper bound. So why should the bound actually capture anything real? So the worry is that these are artifacts. Embarrassingly, I can tell you that as we uncovered more and more bugs in our proof and changed the bound and added terms, I always recomputed these plots, and they were still like this.
Well, no, I'm not worried it's an artifact. I'm saying that perhaps that for most reasonable measures of norms of the weights, you also get the same picture. So it is some margin. It's just not clear which normalization is fundamental.
Yeah. So I don't know, but it's entirely possible. Okay, but so this was these were my loose personal reasons for why I personally found it to be an interesting and good goal to try to prove this margin maximization property. So again, this part of the talk was just to motivate why I think it's interesting and valuable to prove that we're doing margin maximization in the algorithm. Because you could just make your goal proving zero training error or something like that. Or zero testing error or something, or close to zero testing error. Okay, one more comment is that I'm sure everybody has seen all the papers appearing on arXiv that are recently proving under various settings low training error and even sometimes low testing error for deep nonlinear networks. And if you look at these proofs always work with, they overparameterize, unless I'm missing something, a lot of these papers, they assume a very wide overparameterization, and you can check empirically that this causes the weights to change very little. Now, by contrast, today, the result I'm going to give is asymptotic. It talks about the regime of the number of iterations going to infinity, and all the weight matrices go to infinity. All the norm of the predictor goes to infinity. So it might seem a little bit at odds with some of these recent papers that are all in this setting of the weights hardly changing, and then you stop the optimization at a very early iteration. But for reasons I can go into if you wish, these are sort of complementary. There's like the early time scale and the late time scale. And yes, that's one comment. Also, this question of can you prove the algorithm does margin maximization? So you can prove that you get the exact margin maximizer in the case of boosting or coordinate descent. But there the question of normalization was much more simple. You can just do norm duality, and it's a linear predictor after all. So in that case, the normalization was much simpler. And also, there was, of course, the talk by Nati on Sunday, which treated, this is also this topic, implicit generalization. So there were already a lot of comments by Nati on this topic. OK, so next we'll hear from Surya, though, the talk after this is also on this topic. So you will get a fair dose of these sorts of ideas. OK, so that's all I wanted to say about motivating this question of margins. So the real meat of the talk will be actually proving and discussing these optimization guarantees. And so the first one I'll give is just purely in the convex case. I'll discuss in just the regular one-layer linear case the fact that you get this max margin predictor. And OK, so again, our goal is to prove that gradient descent on logistic loss or similar losses finds, in the linear case, a low complexity network, which just means a small L2 norm, so it finds a max margin predictor. And I should say that even though this is a convex problem, this is not a textbook theorem. I don't know of any textbook that has anything that can easily imply any of, even though it's a convex problem, it is absolutely not is not solved in any sense. Okay. And if that's unclear, then I'll explain exactly why. So let me give you a little bit of detail on this problem and why it is not exactly in any textbook. So let's go back to the toy data I had at the beginning of the talk. So the toy data at the beginning of the talk, I had two classes, plus and minus, red and blue, and they were just concentric. I had just circles. And here in this example, I start with the circles being concentric. So again, this is just these concentric circle data. And by symmetry argument, you can just tell yourself the solution to this problem is 0. The solution has a global optimum. The global optimum is 0. Okay? So by symmetry, it's 0. Now, what happens as I start to move the circles apart? So again, I have these positive and negative classes. By symmetry, the solution is 0. As I move them apart, the global optimum moves in one direction. Okay? And there are a variety of ways you can argue that this problem is strongly convex, if you wish. So it's a textbook theorem. It's strongly convex, textbook theorem. The module of strong convexity is dependent on the data, but it is a strongly convex textbook theorem problem. OK, so does everybody see where I'm going with this? So you keep moving the data apart, and you get, oh, and this green line is the path of gradient descent. And you get to here. The solution's at infinity now. It's just like minimizing e to the x. What is the optimum of e to the x? It's at minus infinity. So the solution here is at minus infinity. And in classical learning theory parlance, this is the separable case. So the solution is at infinity. So this is the strongly convex case. This is the case of the solution being at infinity. So it's still a convex problem, but if you try to use a textbook proof here, you will incur all these dependencies on the distance to the optimum. And you need an argument to say the distance is small. So again, we're trying to get to the deep linear case, but I just wanted to show everybody that already in the convex case, this gets kind of complicated. And let me just refine it a little bit. So what I'm doing here is, so that here's this case for the solution set infinity, and I'm just going to add a bunch of data in the middle. Okay, so I've taken a bunch of blue and red points, thrown them in the middle, and what I can do is I can move them apart. And as I move them apart, I'm on that subspace through 0, I'm actually changing, if the data were just there, where the global optimum would be. So the effect is to shift the gradient descent path upwards or downwards. So I have a little bit of superior, incredible technology here. I have this rotation so that you can see what's going on here. But I hope everybody's very excited about. So in general, so how do we characterize the optimum of this problem? So for e to the x, the solution you could just say is at minus infinity. For this general problem, for this general version of the problem, it's not sufficient to say that the optimum is in some direction. You actually have to specify also this offset. So in general, for these logistic regression problems, the solution is a ray. It's a ray that has some fixed offset and then a direction. And as I rotate, you can see this ray better. Okay, so there's a two-part theorem I can give here. And again, we're still just in the convex case. So the two-part theorem, the first part is just the risk. So just the reduction in empirical risk. Nothing about that ray, nothing about the actual characterization of the optimum. And it follows a 1 over t rate, but the point is that there is no hidden dependence on the distance to the optimum. So I can take the step size to be very large. I can take a constant step size, and the rate is still 1 over t. And let me also say that you can prove a parameter convergence guarantee. So again, I should say that this problem does not have strong convexity, and this problem does not have an explicit regularizer. So superficially, it does not have a unique optimum. But as in those pictures, we can characterize exactly what gradient descent is doing. And again, just look at these are all the conditions in the theorem. So the set of conditions are, I'm just requiring the iterates to be bounded. I'm not assuming a bounded global optimum. I'm not assuming strong convexity. I'm not assuming all these things. So I'm just saying the data is bounded, and there always exists a unique ray, just like that purple line before. There always exists this unique ray defined by the data, so that gradient descent follows this path. Okay? So the purpose of this part of the talk was to say that even in the case of linear logistic regression, the convex problem, there were interesting things to uncover in this case that the optimum is not bounded. Let me also say that there is prior and a lot of parallel work here. Nati and a bunch of colleagues, they analyzed this just in the separable case, but in the separable case, they were able to obtain a faster rate of convergence. So instead of it being like a 1 over log t convergence, it's a 1 over log t squared convergence. And in Nati's terminology, this is this implicit regularization setting where what we're saying is that logistic regression, this path it's following sort of the optimal path. So for many years, I was puzzled by the fact that in practice, it does not seem like constrained optimization in machine learning is used that much. And there could be many reasons for this, but perhaps one reason is that gradient descent with an appropriate choice of loss is already solving some of the constrained problems that we wanted. And I won't go through the proof because I want to make sure that I spend enough time on the deep linear part of the talk. But maybe since the videos are recorded, I'll just flash these 2 slides of the proof. Well, I'm extracting these 2 parts of the proof because 2 of the key parts of the proof are very simple and intuitive. To prove this margin maximization, albeit in the slower rate than what Nati gets, there's a trick proof using the Fenchel-Young inequality, which this is basically the entire proof. So I'll just flash this. And the other thing that I will flash is that I was saying that there's this unique ray defined by the data, which so there's this unique ray that gradient descent follows, and you can just given data, you can construct this ray using a greedy procedure. You just sort of greedily build up the largest part of the data, which is separable. So for people that want to, or you can ask me afterwards. But the thing I really want to get to is the deep linear part. Okay, any questions on the second part of the talk? So we had a lot of questions in the margins, and then maybe people weren't fully satisfied. So please reintroduce all your question desires. So in the deep linear case, so here's the predictor. Once again, the predictor is a multilinear form or a simple polynomial in the weights, but it's linear in the covariates. And just some prior work on this problem. So it does have some saddle properties for the squared loss. Here we're using the logistic loss, and that is relevant amongst other reasons that it has the optimum at infinity. And it is known by prior work. So I'll mention it a little bit more. So Surya, I think, will mention at least on the side, she's going to talk primarily about another result, but she'll mention on the side that if you assume the data is linearly separable, if you assume the risk converges, and you assume that the gradients converge, that you find the margin maximizing solution. So our goal today is to build up to that theorem I gave at the beginning, which was that not only do you find a margin maximization, not only are you maximizing the margin, but you're also minimizing these Frobenius norms. And on the technical side, we want to see if we can reduce as many of these assumptions as possible. OK, so let's go back to these pictures. So here's the picture I showed you at the beginning. So there's the blue line, which is the gradient descent path of a one-layer linear network. And then there's the orange line, which is a four-layer linear network, where I'm just drawing the two-dimensional predictor. So we would like to understand what these individual weight matrices are doing. And so the first comment, of course, is because it's logistic regression, the solution is off to infinity. So we know that at least one of the weight matrices is going off to infinity. So now, what are all the individual layers doing? So if you plot the I think spectral here, yeah, spectral norms of all the weight matrices, they also all go to infinity. So initially, this may seem surprising. There's a theorem by Jason and Jason Lee and Simon Du, who are both here, that I'll mention that actually explains why not only do they all go to infinity, but they stay in lockstep. You'll notice that not only are they all going to infinity, they're all going to infinity just exactly together. So I'll mention this in a moment. But so far where are we? So we know these are all empirical results, of course, so far. So we know that the solution is infinity. We know that it's following this max margin path. And now we're trying to analyze the individual weight matrices. We know now that all the weight matrices go to infinity. So here is the plot related to this Frobenius and spectral norm. So I was just saying that all the spectral norms go to infinity. But now, since we are just learning a rank 1 predictor, we're just learning a linear predictor, there's no purpose to having a lot of stuff in each of the weight matrices other than the first rank. And so what's plotted here are the spectral Frobenius norm ratios. You can just plot this. You can just check it. It's really just it's just ignoring all the other singular vectors in each of these matrices. OK, so what do we know so far? We know that the solution is off to infinity. We know that all the weight matrices are going off to infinity. And we know that all the weight matrices are becoming asymptotically rank 1. We know that the Frobenius and spectral norms are, oh, sorry, this is only empirical so far. But empirically, they are all going to, spectral Frobenius norms are going to 1. So now the question is, what are those matrices actually converging to? So if the matrices are becoming asymptotically rank 1, and you multiply them all together, if the left and right singular vectors of adjacent matrices are not the same, then you're kind of killing off norm every layer. It just seems kind of strange. It doesn't seem useful. So this is where the title of the talk comes from, and that's that these adjacent weight matrices are actually aligned. So maybe I should just write this on the board right now. So here's the predictor. And what I'm saying is that this becomes a bunch of, this becomes asymptotically rank 1. So I get all these rank 1 matrices. And moreover, what I'm saying is that they're aligned so these things become asymptotically equal. So asymptotically, is there a question?
So all of them are just equal to the same vector?
Not, well, we can introduce rotations between all the matrices, so there are all these different solutions, but yeah, but asymptotically they all become equal. So there's no norm lost. And actually, everything I've said so far, from here you can reverse engineer this minimum Frobenius norm property from here. This is actually the only way to get the minimum Frobenius norm. So let me just write down that last thing. I mean, there's a slide on this, but so yes, this is what I mean by alignment. And let me show you, sorry?
By the way, you don't even need the Frobenius norm. I mean, gradient descent already has this one of our thing.
Well, that's what I'm proving.
Just gradient descent. You don't need the Frobenius norm.
Yeah. Yeah. I haven't given the theorem statement yet, the full one. But, and here it is in pictures. And I should say that, I mean, it seems like people are less excited about these pictures than I was, but I basically had a 24-hour stretch where I just produced one plot after the other. I just plotted everything I could think of, and I kind of felt like I was going crazy as I started seeing all these patterns coming out. So I want to show you this alignment in pictures. Now, what it means in pictures is that here is the data that I was generating all these other plots from. It's these two concentric circles. If I look at the first layer, so the input data is in 2 dimensions. If I look at the first layer and I plot its first right singular vector, this thing already becomes the max margin predictor. So the first layer already learns a max margin predictor. Now if I map the data through the first layer, okay, I'm mapping the data through the first layer, it looks like this. It squashes it because it's already doing margin maximization. It's projecting it onto asymptotically a linear, a one-dimensional problem. And this one also learns the max margin predictor for that layer. And this is consistent with what I was saying here. So it's learning a max margin predictor at every single layer. So this is another way. I'm giving you essentially 3 ways to state this alignment result. The first one was that minimum Frobenius norm, that's the Frobenius min norm problem. The second one is this per layer margin maximization property. And then finally, I'll give you the real theorem. So here's the real theorem with all the assumptions stated. So assume the data is linearly separable. So it's very important that I'm assuming linearly separable data. So when I did the convex part of the problem, I showed you this sort of painfully refined version of the problem where the data was not separable, or it could be separable. There was all the possible cases. This time, I'm just assuming it's linearly separable. So linearly separable data, and there are a couple of different ways of stating our initialization assumption. Our initialization assumption is that one way to state it is that the initial risk is less than the risk of the 0 vector. Okay, so we're not doing random initialization. You can get to this with just a couple random samples, with a couple random initializations, but we're just assuming that you start with a risk that's better than the 0 predictor. Non-stationary means, I should have written that out. That just means that you don't start at a saddle point. And this holds either for the gradient flow or a gradient descent with a very small decreasing step size and the logistic loss. Okay, so those are the assumptions. And so these have all kind of appeared in the last couple slides. The first one is that the risk does go to 0. The Frobenius norm of all layers goes to infinity. The Frobenius, the spectral norms go to 1. The matrices are asymptotically rank 1. So the UI, VI, those are the top singular vectors, left and right singular vectors for those layers. The product of the Frobenius norms matches the Frobenius norm of the product, and that's because of this alignment property. And lastly, if you use one more technical assumption, so if you assume that the data is not only separable, but that if you look at the points that lie on the that support the margins, then those are full rank. So it's technical assumption. Then we get this max margin predictor. Okay, where W prod is the product of all the weight matrices. And this implies the thing I said at the beginning, which is this minimum Frobenius norm property. The way you get that is by all the matrices being aligned and all that. Okay, so that's the result. Any questions on this? And let me just give a couple comments on the proof, and then we're done. So the first one, maybe this might seem like useless advice, but this is from all my time sweating over these problems and just feeling like they're very difficult. Actually, the main advice I have is very basic. It's that you get a lot of mileage just by writing down the derivative. So by writing down the gradient for these, in linear case, of course, but also in the general case, you get a lot of mileage. So so here is the gradient of the risk. It's that expression at the top. And the first thing you notice that it's rank 1. So if you look at all those matrices that are transposed, if you look to the left of the gradient of the risk term, that's a rank 1. That's a column vector, and everything to the left of it is a row vector. So it's rank 1. So since the gradient descent is just accumulating a bunch of rank 1 things, it's unsurprising that, or it's believable that it ends up having a rank 1 parameter vector. Now, if you take this expression, you just multiply it by the left on the left and right by two different matrices, then you get this expression, this WI gradient with respect to WI, then gradient with respect to WI minus 1 and WI minus 1. So this has appeared a couple times. I don't know who was kind of first on this, but it's appeared a bunch of times. And so this, if you push it through for the gradient flow, implies that all the weight matrices have the same essentially the same norm. The norms are close to each other, and that's why all the norms were in lockstep in those plots. And if you do a little bit of math on this expression, you get also that the singular vectors stay aligned. And the other thing I want to say that was kind of interesting in the proof was that if you assume any one of the properties in this, it's very easy to prove the other ones, but it's actually hard to break the cycle. It's hard to just prove all of them. They all have to kind of go in parallel. If you noticed in the plots, all these quantities are going together in parallel. If I plotted also the risk on these plots, the risk goes the same. The risk curve looks kind of like the norm curves. They all just go together. And to break the cycle, we used this rank 1 property very crucially. So you can ask me about this offline. But the paper basically has this first lemma that says that one weight matrix goes to infinity. And that's kind of a cycle break. Once you have that, then all the other property, this part is a little technical. After that, all the other parts are a little more intuitive. Okay, we can take questions.
Do you know what happens if you have multiple output layers? Output units?
Oh, yeah. So, yeah. Maybe I should repeat the question. So this is.
With all the matrices converge to. Yeah, that's the overall. But you know the precise behavior of the subspaces in each one.
Yeah. So let me repeat the question. Let me repeat the question. So, and maybe Jason knows the answer already. So, the question was: this is in the binary classification. What happens in multi-class? So the proof, which crucially uses this rank 1 property, breaks down. And Ohad asked me about this yesterday, and for some reason I thought I had a proof from months ago. I don't. So I don't actually know how to prove this in the multi-class case.
I don't have a proof. I think I know.
And Jason thinks he knows how.
Yeah, I guess. Because it doesn't follow directly or.
Is there another question?
Any other questions while we're writing the paper over here?
Did you say anything about polynomial
Polynomial networks or nonlinear networks?
Yes.
Wait, which one? Nonlinear networks?
Just nonlinear, but specifically say just polynomial.
So polynomial activations?
We can.
No, the only thing I can tell you about are nonlinear in general, like the general case.
So if it's
No,
just,
polynomial networks in practice are just as powerful as for the usual classification.
No, that's not true.
Not for
Universal approximation holds if and only if your activation is not a polynomial. Oh, okay, okay.
All right, so let's thank Matus again. We'll take